Hello everyone, welcome back. In this video, I shall be building a model for a particle that is falling through a viscous medium. And by a model, what I mean is to write down a differential equation that explains and mimics this phenomena, and by solving which we can find the details of the motion as a function of independent parameter, in this case, time. So in simple words, we'll be writing down the differential equation for this particular problem, and by solving the equation, we shall be able to trace out the details of the motion. That's what we mean. So let us now find out the parameters of the system. Since we're talking about the motion of a particle, we know from Newton's law, the mass of the particle is always involved in determining the motion. So if we have a particle, let the mass of this particle be m. Since it is falling, and I'm assuming it's falling due to gravity, therefore we'll also need the acceleration due to gravity, and that is given by the g that we usually take. In this case, I'll take it to be 9.8 meter per second squared, but in general I'll write just g, and if I need to substitute, then I'll substitute this value, otherwise I'll keep on writing g. Now, it has to take account of the viscosity of the medium, since it's not a freely falling particle. So there is viscosity in the medium, and whenever we have viscosity and a particle is moving through such a medium with viscosity, it will experience the drag force. And the drag force is determined by something which is called the drag coefficient. So the drag coefficient in this case shall be denoted by gamma, and that is the list of the parameters of this system. Of course, in order to solve this thing, we'll need to write down the equation of motion, which is basically Newton's second law, that will give us the required model. In other words, the differential equation that we have been looking for, and the parameters of those equations should be m, g, and gamma, and presumably in this example all of them are constants. So the equation of motion in this case will be dictated by the Newton's second law, which is often written as F equals ma. This is a one-dimensional problem, so we don't have to run into the convention of vectors, and of course a is the acceleration, which is m times dv dt, and this F is actually the sum of all forces. In this case, there are two forces in action. One is the force due to the acceleration of gravity, and the second one is the drag force because of the viscosity of the medium. So let me draw the diagram which will help us to find out the forces acting on the mass. Here on the right, I'll draw the diagram. So this is the particle of mass m, and it is falling downward, so therefore the acceleration is in the downward direction, and the acceleration due to gravity is also directing downward. Now, if the particle is moving in the downward direction through a viscous medium, then the reaction force, which is the drag force, will be acting against the motion, in this case against the velocity, and that will be in the upward direction. So this will be the force, but it is the drag force. And when we write down the net force will have to consider both of these. So therefore, we can write m times dv dt, which is the mass times acceleration, equals the weight, which is mg, and of course the drag force, but it is acting against mg, so therefore it will have a minus sign, and that will be fd. As we know, the drag force is proportional to the velocity and it opposes the velocity, so therefore we can write fd equals some proportionality constant gamma, which is the drag coefficient, times v. So in this case we have m dv dt equals mg minus gamma times v. And this is the desired model we were looking for. We can reshape this equation by dividing everyone by m. So therefore the final form becomes dv dt plus gamma divided by m times v minus g equals 0. So this is the form of the differential equation that we have been looking for. Notice this equation involves only velocity as a function of time and not the position. So the whole equation is a differential equation of the function v of t. Let us now solve the differential equation. Of course, in terms of v, this is a first order differential equation, so we're about to find out what the explicit form of v of t looks like and what would be the freedom in the solution and how can we put the solution in a more physically reasonable form. So this is what we are looking for, right? This is our desired function. What we can do is, number one, we can guess the solution, and yes, guessing is a legitimate way of getting the solution out of any differential equation if you can guess correctly and if you can guess all the possibilities for the candidates of the solution. Then and only then you can find out the complete set of solution by guessing. But fortunately in this case, this equation here looks pretty simple, and so we'll be trying to morph it into a form which will preferably be integrable at an instant. So this is what we're going to do, right? So what we're going to do is to keep the differentiation term on the left and send everything to the right. So you get negative gamma divided by m, and then we have v plus g. Now I'm going to play a trick here. What I'm going to do is I'm going to factor out gamma divided by m from both of these terms sort of forcefully, right? So that this term, despite not having an explicit gamma divided by m term, we're going to factor out gamma divided by m from this term as well, which results in v, and then in order to account for the positive sign we need to put a negative sign inside, and then we'll have to write m divided by gamma times g. Notice if we multiply negative gamma divided by m with both of these terms inside the parenthesis, then of course we'll get our previous expression back. Now we can do something pretty interesting. Notice the second term on the parenthesis, which is negative gamma divided by m times g, it's a constant, right? So what we're going to do, we're going to define a new variable. In other words, we're going to change the variable So what can we define it into? So let me call it f, and f would be equal to v minus m divided by gamma into g. Now, of course, we can take the derivative. So df dt is going to be equal to dv dt. Okay, because the derivative of the constant is going to be 0. So, applying this fact, we can come back here and rewrite this equation in terms of f instead of v. So we get df dt, and on the right hand side we have negative gamma divided by m into f. So now we can write the corresponding equation in terms of the differentials, right? So we can write df over f equals negative gamma divided by m and then dt. And dt and df are differentials. In ordinary differential equation we can do that, and of course we'll have to integrate, and when we integrate on the right side, negative gamma divided by m being a constant stays out of the integration sign. They can also come in, but they don't influence the integration process, and therefore what we're going to get is, on the left hand side we're going to have log of f. Basically we are not doing integration, it's an anti-differentiation process, and we want to write down the solution in the general form. So we have natural log of f equals negative gamma divided by m and then t. Of course we have to write down the integration constant, which we need to place whenever we carry out anti-differentiation process. So I can just write plus c, that's fine, right? And of course instead of f we can now substitute v minus m divided by gamma into g, and that would be equal to minus gamma divided by m t plus capital C, which is the constant in this case. Of course we can invert the logarithmic function, so we get v minus m divided by gamma times g equals the exponential of negative gamma divided by m into t, and then we have e to the power c. And of course c being a constant makes e to the power c another constant, and so let me call it some lowercase c, right? So these are uppercase c's and this is a lowercase c. I wish I had a better handwriting in order to distinguish between the two, but I don't, so let's roll with it. E to the power negative gamma divided by m times t. Okay, fantastic. So what else are we going to do? We're going to write v equals m divided by gamma into g plus c times e to the power negative gamma divided by m into t. So, have we found our solution? The answer is no. Why? Because now we need to insert the initial condition. So assuming that initially at some time, it can be t equal to 0, it can be t equal to some t naught, whatever it is, we have to choose the initial condition according to our convenience or the given physical problem. Now, since we're purely under mathematical interest, so let us call, just because of the convenience, the fact that v at t equal to 0 is v naught. So if that is the case, and if we insert that into this equation, what do we get? We get, so at t equal to 0, v equals v naught. On the right hand side, we get m divided by gamma times g, and then plus c. Actually, it's going to be a lowercase c, so c, and then e to the power negative gamma divided by m times 0, so e to the power 0, which is just 1. And of course, this gives us the explicit expression for c, which is v naught minus m divided by gamma times g. So if we plug that in here, what do we get? We get v equals m divided by gamma times g, and then plus v naught minus m divided by gamma times g times e to the power negative gamma divided by m into t. So that should be our general solution for this problem. Of course, if we want to find the position as well, given in a given time, then we'll have to integrate it again. Now, of course, the solution is a differential equation, but the fact that v is actually the x dt, where x is the position and also a function of time. So therefore, instead of the left hand side, we can now write dx dt and then integrate for t. So the basic process is treat the differentials like the fractions, and so when we integrate the left hand side, we simply have dx dt times dt. On the right hand side, of course, we have integration being distributed over the plus sign, and so we have m divided by gamma times g dt integration. Well, anti-differentiation, but I'll continue to refer it as integration if that's not a big problem. And so here we have integration over v naught e to the power negative gamma divided by m times t dt, and then of course negative m divided by gamma g e to the power negative gamma divided by m t dt, and integration as well. So in the left hand side, we are left with x of t, and on the right hand side we have m divided by gamma and then gt. Then we have v naught, so v naught, and then e to the power negative gamma divided by m t, negative m divided by gamma due to this exponential factor here, and also we have positive because we have two negative signs, so m divided by gamma g, and then e to the power negative gamma divided by m times t, and then of course m divided by gamma. All right, and also a important part, which is integration constant, capital C, this time a prime. So do we need to rewrite this? I think it would be not a very bad idea. So first of all, we have m divided by gamma gt, and then minus m v naught divided by gamma, and then we have the exponential factor e to the power negative gamma m t, and of course we have plus m squared divided by gamma squared g e to the power negative gamma divided by m t, and then plus c prime. Now we need another initial condition in order to find out the expression for c prime. So for simplicity, let us take the initial condition that when time was 0, the point the object started to fall from was dubbed to be the 0 point. So of course, if the object is going downward direction, we'll get continuously bigger and bigger negative number. So that means smaller and smaller number, right? Because that's bigger in the negative direction. So then our equation would become 0 equals, well, on the right hand side we have negative m v naught divided by gamma, and then e to the power negative 0 is, well, this whole factor is 1, and then we have plus m squared gamma squared in the downstairs times g, and then plus c prime. Well, this results in c prime equals m v naught divided by gamma plus m squared divided by gamma squared times g. Okay, that's interesting. So if we plug those in into our solution, what do we get? We get x of t equals m divided by gamma gt, and then minus m v naught divided by gamma e to the power negative gamma divided by m t, and then of course plus m squared gamma squared and then g e to the power negative gamma divided by m t plus wait, I messed up with a negative sign, I guess. Yeah, this should be negative. So negative. So we have m v naught divided by gamma minus m squared divided by gamma squared g. If you rearrange this, what do we get? We have this very interesting solution, and that is due to the initial conditions that we have chosen. Had we chosen different initial conditions, we would end up with a different form. But you can now play with this solution by taking it to different extremes. So for example, what happens at t equal to 0, what happens at t tends to infinity, etc., etc., and that will sort of give you an idea about the process, and then you can compare it with your intuition, if that makes any sense, and most likely that is going to tell you all the physically intuitive phenomena that you can think of and more. And that is the amazing effectiveness of mathematics, is that if you feed in everything logical and related to reality, it will eventually take you to a real physical answer. So let me end this video here. It's a long video, but I hope this sort of gives you an idea about the systematic process of solving differential equation, and we'll be formalizing this process step by step in the following videos. Thank you very much.